All right, welcome to another stats warm-up. Let's see what we have here. So in baseball, a 300 hitter gets a hit 30% of the time. When a player hits 300, fans tend to be impressed. Typical major leaguers bat about 250 times and hit about 260. Assuming a hitter's successive tries are independent, could a typical major leaguer hit 300 just by chance? In short, calculate the probability of getting at least 150 hits in 500 tries if your probability of success is 26%. All right, now the key here is focusing on this phrase, at least 150. That means I could get 150, 151, 152, all the way up to ... getting 500 hits in 500 tries. Super unrealistic, but whatever. So the odds are, we're trying to find the odds of, all of these together. We're not just finding the odds of getting exactly 150 hits, we're saying 150 hits or more. Now, we wouldn't want to have to go through and do a binomial PDF for each of these. I mean, we could do a binomial PDF for this, add it to this, add it to this, add it to this, and so on and so forth. But instead, we're going to do 1 minus. So we're going to do 1 minus binomial CDF. All right, and the reason we have to do 1 minus is because binomial CDF automatically goes from a number down, and this time we need a number up. So we're just kind of taking advantage of the complement. And we start with the number of trials. So there were 500 trials. The probability of success, we said, was 26, so 0.26. And then even though we're doing at least 150, we're going to put 149 in this last spot. Now, why are we putting 149? Because the BCDF is going to do 149, 148, all the way down to 0. So if we subtract away 149 to 0, what's left is 150 to 500, which is what we actually need. All right, so that's the explanation. As far as actually calculating it, it's just 1 minus binomial CDF, which is going to be down towards the bottom here. There are 500 trials. The chance of success is 26%. And we're going to type in 149. All right, and we get a chance of, 2, 4, 6. So basically, there's a 2.5% chance that a league average hitter could just get lucky and end up with an average of 300 for an entire season. And everybody might be excited and think that they're a better player, and it might just be that they beat the odds and we're that lucky 2%. All right, so again, main thing here is just this idea of when you're doing a number and up, we have to do 1 minus. All right, engineers define reliability as the probability that an item will perform its function under specific conditions for a specific period of time. A certain model aircraft engine is designed so that engines have a probability of 0.999 of performing properly for an hour. Company engineers test an SRS of 350 engines of this model. Let X equal the number that operate for an hour without failure. What is the mean? What is the standard deviation of X? All right, so these are 2 formulas that you do need to know. All right, the mean is found by doing N times P. The standard deviation is found by doing the square root of N times P times Q. So what are N, P, and Q? N is going to be your sample size, so that's the 350. P is going to be your probability of success, so that's the 0.999. And then Q is just always 1 minus P. All right, so our mean is going to be 350 times 0.999, or 350 times 0.999, 349.65, 349.65. Our standard deviation is going to be the square root of 350 times 0.999 times, and then 1 minus 0.999 is just 0.01. All right, so that would be our standard deviation right there. And we end up with 0.5913. All right, so we've got our mean, we've got our standard deviation. All right, could we use a normal approximation for this situation? So we've talked about how when certain conditions are met, the normal distribution and the binomial distribution will more or less give you the same answer. And the condition required is 10 successes and 10 failures. All right, so the way we find that is we check n times p and we check n times q. All right, so n times p we already did. That was our 350 times the 0.999, and we know that that's 349.65. N times q we haven't done yet. That's the 350 times the 0.001, which is basically just going to move the decimal 3 spots to the left. So we're going to end up with 0.35. So this one is good. This one is not high enough. So because the condition is not met, we can't use the normal approximation. Right? If we tried to use it, it would still give us an answer, but the answer wouldn't be very accurate. All right, so it's a situation that we don't want to get ourselves into. So 2 engines fail the test. You are convinced that this model of engine is less reliable than it's supposed to be. Are you convinced? Sorry. Calculate the probability that X is no more than 348. So that's basically saying 348, 347, 346, all the way down to 0. All right, no more than 348. So the only ones that we're not calculating are 349 and 350. So we're looking at all of these, and we're just leaving out these 2 over here. Now, these are easier than the ones we did up above because this is exactly what binomial CDF does. All right, so we can just use a binomial CDF when there's 350 trials. The odds of success are 0.999, and we want to know 348. All right, that will give us 348 and down, which is exactly what this question is asking for. So binomial CDF, 350 trials, 0.999 chance of success. We want to know 348. All right, so it works out to be 0.0486. So there's only a 4.86% chance that you'd end up with 2 or more engines failing, or put the other way, there's only a 4.8% chance that you'd only end up with 348 or less being successful. Whichever way you think about it, doesn't really matter. Whether you think about it as 2 or more failing or 348 or less succeeding, same thing. Either way, the odds of that are 4.86%. All right, let's take a look at the back. As a special promotion to celebrate International Book Giving Day, Pet Theft Awareness Day, World Sound Healing Day, and National Cream-Filled Chocolates Day, which just happens to be, in case you were curious, this is February 14th. I don't think there's anything else on February 14th. This seems like the best use of February 14th, World Sound Healing Day. So anyways, a soft drink company is running a special contest. The company advertised that 1 out of 6 bottles would win a book giving, pet theft, sound healing, cream filled chocolate related prize. What a pet theft related prize is, I'm not really sure. You and your 6 closest friends love book giving, pet theft, sound healing, and cream filled chocolate and decide to buy a soda. Let X equal the number who win a prize. What is the mean and standard deviation of X? So again, we know that our mean is n times p. We know that our standard deviation is the square root of n times p times q. All right, so n is our sample size. In this case, we have 6 friends. And the chance of winning or being successful, actually, sorry, we don't have 6 friends. It is myself and 6 of my closest friends. So our sample size is actually 7. And we have a 1 in 6 chance of winning. So down here for our standard deviation, sample size is 7. We have a 1 in 6 chance of winning. So we have a 5 in 6 chance of losing. So we have 7 times 1/6, which is 1.16 repeating. So we'll just say 1.17. And then our standard deviation is the square root of 7 times 1/6 times 5/6, or 0.986 we'll go with. 0.986. All right, so again, just knowing those formulas, being able to say, all right, binomial n times p, square root of n times p times q. Second part, what is the probability that at least 3 of your friends win a prize and have the greatest book giving, pet thieving, sound healing, cream filled chocolate day of their life? So again, at least 3 is implying 3, 4, 5, 6, or 7. Now, this is only 5, so if you wanted to do a binomial PDF over and over and over again, you could do that. You could do binomial PDF for 3, add it to the PDF of 4, PDF of 5, PDF of 6, PDF of 7. But again, it is shorter to use binomial CDF. So if we're doing at least 3, that means we need to take away 2, 1, and 0. If we're able to get rid of 2, 1, and 0, what's left over will be the 3, 4, 5, 6, and 7 that we actually want. All right, so that's going to be 1 minus binomial CDF. There are 7 people in total. The chance of winning is 1/6. And even though it says at least 3, we're going to put a 2 in here because that's going to subtract away 2, 1, and 0 and leave us with 3 and higher. So 1 minus binomial CDF. All right, this time we only have 7 trials. The chance of winning is 1/6. And I'm going to do 2. And this will calculate 2, 1, and 0. And then we're subtracting that away. So we're left with 0.0958. 0.0958 as our final probability there. Okay, number 4, one way of checking the effect of undercoverage, non-response, and other sources of error in a sample survey is to compare the sample with known facts about the population. About 12% of American adults identify themselves as African American. Suppose we take an SRS of 1,500 American adults and let X be the number of African Americans in our sample. Is X approximately a binomial random variable? Yes. I kind of jumped ahead of it there. I was supposed to say Y, and then I'm going to say, yes, it is, even though we're sampling without replacement, $1,500 is less than 10% of the US population. So we're okay. All right, so we have these two different rules. One is your sample less than 10% of the population? All right, that rule deals with independence and sampling without replacement. The second rule we have is, can you use a normal approximation? And these are two separate rules that have two different applications. All right, you don't need to have both of them. It depends on what you care about. If you care about, is something approximately a binomial random variable, then this is what we need to look at. If you care about, can we use the normal approximation, then you're looking at, do I have 10 successes and do I have 10 failures? All right. In this case, we're surveying 1,500 people, and the chance of being African American is 12%. All right. We're surveying 1,500 people. The chances of not being African American would be 88%. So if we go 1,500 times 12% and get 180, and we do 1,500 times 88% and get 1,320, in both cases, we're above 10. So in this case, yes, we can use the approximation. Both are over 10. All right, so again, sometimes students get these two confused, but this deals with independence and sampling without replacement. This deals with trying to use the normal approximation. So now this says, using the normal approximation, find the probability that the sample will contain between 165 and 195 African Americans. And then the hint is, you'll need to start by using what you know about binomial distributions to find the mean and the standard deviation. So that means using n times p, and it means using the square root of n times p times q. All right. So we've got 1,500 times 12%, which we already did in the last problem, and we know it's 180. And then we have the square root of 1,500 times 12% times 88%, and that'll give us a standard deviation of 12.5857. All right, now that we have these, we can do a normal approximation. We can say, all right, NCDF from 165 to 195 when the mean is 180 and the standard deviation is 12.5857. All right, so now we're going over here. Normal CDF, 165, 195, 180, 12.5857. And we end up with 0.7667. So basically 75%, or 3 out of 4. So again, this is just kind of a shortcut approximation that you can do. I mean, we could have done this using binomial CDF. I could have said binomial CDF, 1,500, probability of success 0.12, 195. All right, that would have pasted it in my calculator. That would have done 195 and down, which is too much, but then I could subtract a binomial CDF where I do 1500.12, 164. So if I subtract away 164 and down, then I'm left with just this 195 to 165. And I'm not going to get the same answer. All right, this is 78%. Here I got, roughly 77% if you were to round it, but it's close. All right. And sometimes the normal approximation is easier, especially when you're doing kind of ranges like this. And since it's in the same general ballpark, we do say that, like, okay, it's not going to be exact, but a lot of times it'll be close enough and we can get a similar answer. All right, so again, main thing here is understanding how to use binomial CDF. Situations where you're getting a number and up, situations where you're getting a number and down, and just being able to differentiate between those two. Also, knowing these formulas is important, and then knowing these different tests. When are you allowed to use a normal approximation versus when you're not, based on this 10 success, 10 failure, and then the sampling without replacement test. All right. So as usual, if you have any questions, let me know. Otherwise, best of luck.